Okay, hi, TIC or BC Part 1. This is for your work on Friday, February 2nd, and this is the long period, and you should have hopefully some kind of headphones and your screen, okay? This lesson, or our class today, is going to be divided into two areas of focus. One, we're going to continue looking at limits. Limits has been our life recently. I know you feel that way. But now we're going to look at limits and just see if we are able to work with limits when, we have a slightly different presentation here in terms of that variable which is doing the limiting, and also in terms of what we are taking the limit of, or the argument of the limit, for so to speak. Okay, and here you also will see us talking about the limit of a function, where that function is defined as the inverse of a function. So some of this we're going to work together for the first couple here, and then I'm going to give you a few to work on. And then what I want you to be able to find is this piece of paper right here. We're going to go there and work on that as well. So we have a pretty full day today in class. Okay, so let's take a look at this. This limit looks slightly different in that, number one, the argument of the limit has two variables. But if I were to ask you the variable of the limit, what is the variable that is doing the limiting action? Of the variables x and A is approaching 2. And if A is approaching 2, there's nothing below in this subscript here talking about what x is approaching, so A is approaching 2, and if we kind of use the rules that we have used with limits thus far, we are going to check and see if we can evaluate this limit by plugging in A for 2, or 2 for A, and the limit here is 3x squared minus 4x plus 12. Okay, and this is the limit. So here is the first time we're seeing a limit not equal a number per se, or not equal, say, a positive or a negative infinity, in which case it would not exist, but there is a possibility that a limit could result in a function. Okay, so the result of a limit could be a number. We've seen those. The result of a limit could be a non-finite entity, like positive infinity or negative infinity. But this is the first time here we are seeing the result of a limit be a function of x. Okay? This is another interesting one here, right? Here we're saying that x is approaching not a number, but x is approaching h. And if I look at this, look at the argument of the limit here, I have two variables, x and h. So x is approaching h. And the first thing we're going to do, which should hopefully not surprise you, is input in x approaching h, and this will give us 3h squared.
Hello.
Times, Justin, I'm giving a screencast, honey. Times the sine of 0, all divided by 0, which equals then 0 over 0. And as we know, with 0 over 0, we have to look back and see if there's a way that we can manipulate this limit. Well, hopefully your eye is drawn to this right here. And specifically, the fact that I could rewrite the argument as 3xh times the sine of x minus h all over x plus h times x minus h, because after all, the denominator is just a difference of squares, right? But then I think you see that this portion equals 1. So now when I go back and address the limit as x approaches h of all of this then will equal 3h squared all over 2h, which then simplifies to 3h over 2. Okay? So if you look at these limits, there's nothing new in the math of the limits. What's new is possibly the result, right? The result could be a function of x. We could look at limits where that variable which is doing the limiting is approaching not a number, but another variable. Okay? We can also take a look at evaluating limits where the argument of the limit is in function notation. So in this case here, as x approaches 3, of f of x plus 6 minus f of x all over x plus 2. Let's see what we can do. This is going to equal f of 9 minus f of 3 all over 5. And that's all we can do. We don't know what f of x is. We can't actually evaluate f of 9 or f of 3, right? That's it. So it's possible for an argument of a limit to describe something or in function notation, right? And the final one here, the limit as x approaches 7 of g of x, where g of x is defined as the inverse of f of x. Be very careful on the cumulative mid-year exam. Some of you confused this with this. Okay, these are not the same thing. This is saying the reciprocal of f of x. This says the inverse of f. Go ahead and do this one on your own and then replay me. So I guess the question here is, how many of you went about this question by saying to yourself, well, I found f of x, and then you maybe drudged up your notes. Oh no, you would never do that because you have all this in the back of your head because we just had a mid-year exam. So you would not have to drudge up your notes. How many of you looked at f of x here and you wrote this as y equals 3x plus 2, you swapped x and y, and then you solved for y, and therefore you got the function for g of x, right? And then you took g of x and replaced g of x in the argument of the limit over here, and then found the limit of g of x as x approaches 7. That would not have been wrong. However, I invite you to look at the following. F of x equals 3x plus 2. On f of x, y equals 7 when x equals 5/3, right? So 5/3 comma 7 is a point on f of x. 5/3 comma 7 on f of x corresponds to 7 5/3 on g of x. F of x is a linear function. G of x is a linear function. Therefore, as x approaches 7 on g of x, we know this limit must equal just 5/3. So while you could go ahead and swap x and y and find g of x, this allows you to not only save some time, but just kind of begin the practice of, knowing when there are multiple ways to go through a solution and they're all equally valid. There's a case to be made sometimes for choosing that path, which might be more efficient. Okay. All right. Now let's take a look at this. So once again, to recap here, these 4 limits we've done, just slightly different presentations of what a limit 1 could look like, and 2, what a limit could result in. All right? Okay, let's do this one now. So here I've given you a function, a fairly simple quadratic function, parent parabola shifted up 1. And I'd like you to find the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Well, when I go ahead and plug in h equals 0, right, this is the variable of the limit. X is the variable of the function, interestingly. What I do get here is 0 over 0. Agreed? So I'm going to try this now. In this case, f of x plus h and f of x exist because I know what f of x is. So I'd like you to rewrite this with me. The limit as h approaches 0 of f of x plus h is x plus h squared plus 1 minus f of x, which is x squared plus 1. Everyone okay? All over h. Well, I'm going to simplify because here, even if I sub in h for 0, I would still get 0 over 0. I haven't made any progress. But I think I'm going to go now and do this. Limit as h approaches 0 of, all right, x squared plus 2xh plus h squared plus 1 minus x squared minus 1, all divided by h. Now, here's an example of messing around. Oh, I can clean. That was feigned surprise. I knew that was going to happen, everyone. What happens here? X squared and x squared cancels out, positive 1 and negative cancel out, and my argument of the limit becomes 2xh plus h squared all over h. And I am finally done cleaning, aren't I? No, I am not. The numerator, oh, and plus I should say this, boys and girls, maybe you were here and thought, oh, I've cleaned, and you plugged in 0 again to see if this limit gets us anywhere, you would still get 0 over 0. So then you say, is there anything else that I can do? Well, let's see. The numerator has a common factor, h. H and h cancel. And now, let's see. As h approaches 0, what does 2x plus h approach? Ah, 2x. That's quite fun. Now, this limit here, when you find the limit as h approaches 0 of f of x plus h minus f of x all over h, this limit will always result in an indeterminate form. Okay? And this limit we will revisit many, many, many times. Many times. In fact, this limit is so incredibly famous and integral to the work we are about to do on this page over here, this one, that this limit right here actually has a name. This is called, maybe write it over here. When you have a function, whatever the function may be, okay. This piece right here, f of x plus h minus f of x, all divided by h, this is called a difference quotient. Okay, f of x plus h minus f of x, all divided by h, is called a difference quotient. This whole thing, this is really going to surprise you, boys and girls. When you take a limit of a difference quotient, guess what that's called? That is called a limit of a difference quotient. It is called a limit, the limit, or a limit of a difference quotient. A limit of a difference quotient. I know that surprised you. So that's kind of neat. I mean, what we saw here is a difference quotient will always, a difference quotient is always f of x plus h minus f of x all over h. The limit of a difference quotient, and just be careful too, in the limit of a difference quotient, okay, understand something. H is approaching 0, not x. Okay, h is approaching 0. H is approaching 0. A limit of a difference quotient will always initially be indeterminate, and specifically indeterminate of the form 0 over 0. What we did right here, this process, where we started with this problem, and we worked our way through and went through over here to conclusion. Okay, what we did here was we evaluated a limit of a difference quotient, and here I'm saying I'm choosing the word a and not the, because the particular limit of a difference quotient we evaluated here pertain to f of x equals x squared plus 1, right? Obviously, if this function is different, the work here will be different. So in blue, this whole process that we just underwent, this process was called an evaluation of, because we actually found the value of this limit, an evaluation of a limit, not just any limit though, a limit of a difference quotient. Okay, very good. What I'd like you to do before I move forward, just to make sure we're all on the same page, I would like you to do the following. Okay, I'd like you to do this right now. Evaluate the limit of a difference quotient right here for f of x equals root x. why don't you go ahead and try it with someone next to you, or get up and move across the room, okay, and maybe work together. This question here is a fantastic one. You know, everything we do, it just builds incrementally on what we've done so far. And if you'd like a little teaser of a hint, go ahead and play me, and I'll make sure I reveal just little tiny steps along the way. But you can pause me now to give it a first crack at it with someone next to you or on your own. Okay, teaser first. So the first thing I did was I just inputted what f of x plus h and f of x were. And lo and behold, I do indeed get 0 over 0 as h approaches 0. So the question is, what to do algebraically? Okay, well, interestingly here, I see square roots. And my experience with square roots in a quotient thus far has suggested that one algebraic little slick trick I can try is what begins with a C and an O and an N and a J-U-G conjugates. And look at the form of one I chose right here in red. See how it just kind of weaves, everything kind of weaves together? Now, what you need to do is just a little tiny baby hint. Here's where you'd pause me now before I finish the rest of the problem. And of course, if you've already finished and you want to see the rest of it, go on and replay me. All right, well, of course, this is the form of 1, or as Albert says, 1 in disguise. And then this is just algebra. Look at that. Look at that numerator, right? A minus b times a plus b equals a squared minus b squared. And just be careful with just your arithmetic and algebra. The denominator is h times all of this, okay? And I noticed, look at the red. I have some cleaning I could do in the numerator, x and negative x. And I'm left with this, the green, h over h times all of this. Oh, some more cleaning. I always make sure I clean house. Whenever I do an algebraic move to mess with an argument, I always clean house all the way. Then I'm here. These h's cancel. I'm left with 1 over the root of x plus h plus the root of x. Now let's try taking the limit. H subs in for 0, and I get 1 over root x plus root x, which is 1 over 2 root x. Phew, indeed. Okay, so once again, you know, the point of this screencast has been to really show us that all the work we've done with limits just has gotten us to this point of being more flexible with our understanding and playing with limits in their various presentations. I mean, look at how different these all look, right? All of these look so different, so very different. But you know what, boys and girls? The fundamental understanding of what is a limit, how to evaluate a limit, has not changed whatsoever. Fantastic. We're actually not going to go right here. I feel like this is this huge buildup at this point, but you know what? We're not going to go right here because there's something that fits just more seamlessly with this story here. All right, I'm going to move on and continue. Let me get a clean page. All right, so you're going to want some general accuracy here, some reasonable accuracy. And yes, I am switching gears right in the moment because you know what? That's just how I do things, boys and girls. If it makes sense in the moment, we're going to go in that direction. I know it wasn't the plan. I know I've been kind of building up, and I feel like I've built this up so much that when I get there, it's going to be the biggest letdown for you, but that's all right. It's okay. Oh, no, where'd it go? Here we go. What I'd like you to do is just with relative accuracy, go ahead and put down f of x equals 1fx squared. Note my scale just for accuracy. I have these points. I'm looking only at values of x bigger than or equal to 0 in the moment. And what I'm going to do is just, with reasonable accuracy, go ahead and try and connect these points, okay? And you'll be much better at this than I am. Okay, so a couple things. If I ask you to go ahead and find the slope of this line and this line right here. This green line is called a secant line. Okay, I'll call this L. So L is called a secant line. It's a secant line of f of x. And more importantly, when we talk about a secant line is a line whose endpoints are on, I mean, you probably heard the word secant line in the context of circles, right? But in this case, it's a secant line of a function or to a function. Usually I say of a function. The endpoints are on the function. But we say it's a secant line of f of x over the interval of x from 1 to 3. Why? Because x equals 1, x equals 3. Okay? And what I want to do right now is go ahead and calculate the slope of the secant line. The slope of the secant line, okay, y1 minus y2 over x1 minus x2 is going to equal 4 1/2 minus a half all over 3 minus 1, which is equal to 2. Everyone okay with that? And we get 4 over 2, which equals 2. 2 is the slope of the secant line. I hope you're appreciating right now that while we are squarely in the world of calculus, I hope there's a part of you saying, this is nothing new. This feels like Math 1 or even Math 2. And you'd be right. And I think very soon you're going to have the epiphany that all of math that you've done, there really is no demarcation between Math 1 and calculus or Math 1 and Math 2. It's all kind of the same thing. It's all in this big pot. Well, let me give you some context here. Let's say that the horizontal axis is the number of days since school started. Okay, and let's say the y-axis is the number of blisters on your writing hand. Okay, in the context of these two variables, what would you say the slope of this secant line represents? Have a 30-second conversation. I'll give you a phrase. Rate of change. Okay? Tell me what the slope of the secant line represents. Okay. The slope of this secant line, this is a secant line over the interval of x from 1 to 3, right? It is the kind of rise/run, right? From x equals 1 to x equals 3. And I don't think you would, it is too far for us to reach to say that if this, if the y coordinate, the y variable corresponded to blisters on your writing hand, and the x is number of days since school started, the units of this 2 here, this 2 then has units. This is blisters over day. Okay? In other words, the slope of this secant line here, this slope, represents, I'll say it first and write it. It represents the rate of change of blisters per day over the time period or over the interval from day 1 to day 3 of school. But here's the most important thing. It's a rate of change, but more importantly, it is an average rate of change. Okay, it is an average rate of change. On average, between the first and third day of school, the number of blisters on your writing hand increased at the rate of 2 blisters per day. That deserves writing down. Represents an average rate of change. This word here, so important. It's an average rate of change. Specifically, we'd say the following. between the first and third day of school, your number of blisters increased at an average rate of 2 blisters per day. Note the units, right? Blisters per day. Average rate of change. Average, because from day 1 to day 2, for example, you gained 2.5 blisters. Yes, that's very odd. From day 2 to day 3, you gained 2 blisters, okay? But on average, boys and girls, on average, between day 1 and day 3, on average, the number of blisters on your writing hand increased by 2 blisters per day, okay? Average rate of change. Average, average, average. All right, I'm going to draw another secant line here. Here's a secant line. I'll call this secant line M, okay? The slope of secant line M. Go ahead and find the slope of secant line M, and then again, write the significance of that slope of secant line M in the context of blisters and days. Okay, here's the slope of line M. Slope of line M, slope of line M, slope of line M, and then I just made it into a decimal. Okay, average rate of change of blisters on your hand from day 1 to day 2. The units of this number are blisters per day. This means that on average, the number of blisters on my hand increased at the rate of 1.5 blisters per day between day 1 and day 2, or from day 1 to day 2. All right, now let's go back here and do this. In this drawing, here's what I want you to do. I'd like you to do this. Come over here and call this distance H. Let's call the distance between 1, okay, x equals 1 and x equals 2. Let's call this distance H. This distance H also could have been here, right? From x equals 1 to x equals 3. In other words, this distance here, this horizontal distance, the distance from 1 to either point, whether we were looking at this point M or whether we were looking at this point at the end of L, let's just call that distance H. Okay, H is the distance. So H is the horizontal distance from point 1 to whatever other secondary point we're looking at. Does this make sense to you? Whatever second point on the curve, right? Horizontal distance or change in x. Okay, this is horizontal distance. Horizontal. H is the distance between x equals 1 and whatever second point we're looking at. From one point of the secant line to the other point of the secant line. H is the horizontal distance. So let me ask this question. Tell me what happens if we kind of play with this little mental idea. As H approaches 0, what do we start looking at? As H approaches 0, in other words, as H approaches 0, think about it. As H, the horizontal distance, approaches 0, what I start looking at are secant lines that are closer and closer and closer to x equals 1. In fact, they get so close that they start being really difficult to draw, right? In fact, as H approaches 0, these secant lines get so tiny, and this horizontal gap, as it approaches 0, right, the gap starts to close. And if you think about the interval of time that you're looking at the average rate of change, here we're looking at the average rate of change from day 1 to day 2. But then if we look at, this point, on the function, we start looking at the average rate of change from day 1 to day 1.5. Then from day 1 to like day 1 1/8. Then from day 1 to day 1 1/16. Or from day 1 and day 1 1/1000. Boys and girls, what happens is, as H approaches 0, my average rate of change, because this word average rate of change, an average rate of change, the implication is you're looking at a rate of change over an interval of time, right? There's some time there. But as h approaches 0, an average rate of change approaches what kind of a rate of change? What kind of rate of change describes the rate at which something is changing when the change in time is almost 0? The change at not just an interval of time, but the change at a particular single moment in time, right? As h approaches 0, an average rate of change approaches, you know what? An average rate of change approaches what's called an instantaneous rate of change. An instantaneous rate of change. And what an unbelievably fantastic idea. This idea of an instantaneous rate of change. An instantaneous rate of change means I want to look at the rate of change of blisters on my hand, not between day 1 and day 2, okay? Or not, from day 1 to day 3. I want to look at the rate of change of blisters on my hand from day 1 to day 1.0000000, etc., right? I want to look at the rate of change of blisters per day on my hand at the precise moment when T or D equals 1, which is a really wild idea, okay? And what's interesting is, as h approaches 0 and an average rate of change approaches an instantaneous rate of change, tell me what happens to the secant line. So see this secant line here? And it's going to be really hard to draw, right? The secant line approaches what kind of a line, everyone, right? So here's a secant line L. Here's a secant line M. Here's a secant line purple. Here's the secant line as it gets closer and closer and closer. Do you agree that as this point pulls closer and closer and closer to this point at x equals 1, do you agree that these secant lines almost become indistinguishable from the curve itself? Ultimately, you know what happens, right? And of course, I could take these green lines. Let me go back here. Any of these secant lines, I could have extended it. It's still a secant line, right? Okay. Just like M here. M could have been it's the same line after all. So the purple lines, as the point pulls closer and closer and closer, what happens? What do you notice happening? These secant lines, and a secant line, it intersects a curve twice, two times. Like look at line L, intersect the curve once, twice. M intersects the curve once, twice. As this second point pulls closer and closer and closer, boys and girls, how many times does that line cross the curve as the point gets closer? Yes, it crosses it once. So what happens is, as your average rate of change, which is represented by the slope of the secant line, as that average rate of change approaches an instantaneous rate of change, your secant line morphs from being a secant line intersecting the curve twice to what kind of a line is it that crosses a curve just once? A tangent line. Okay? So what's really amazing is, as h approaches 0, an average rate of change approaches an instantaneous rate of change. And a secant line approaches a tangent line. Let's just be clear too. A secant line approaches a tangent line where the point of tangency, right? It's where the point of tangency, okay? Where the point of tangency right, represents the particular moment in time that the instantaneous rate of change is occurring. Does that make sense? Because we're getting closer and closer to d, day, or time, d equals 1, right? So where the point of tangency represents the moment in time of the instantaneous rate of change. No complicated math, no big mathematical numbers or crazy functions, big ideas, very big ideas, okay? So that was, I hope, fantastic. And you know, truth be told, this wasn't the party day, but this is kind of really a big build-up day. But I hope it's, pardon me? No, but I hope it's still fun. All right, I told you that I wanted to make sure I tied up that which we've been doing for the past 35 minutes and 44 seconds. So let's take a look at this. Are you ready? We had this drawing, and here I'm going to do just a rough sketch, okay? Very rough, of, right? Here it was. This is f of x equals 1/2 x squared. All right, this part, we don't have to be careful now. Here is x equals 1, right? When x equals 1. And what we did was here, we're pulling that point, that second point, that secant point, closer and closer to 1, right? All right, well, guess what? We called this distance, right, the horizontal distance between 1 and that second secant point, h, right? Okay, I'm going to do this then. So if this is 1, this is an h. Guess what this is? This is 1 plus h. Everyone agree? And if this is x equals 1, and this is x equals 1 plus h, then what is this? H. The y-coordinate here is f of 1 plus h. Okay? So this point here has an ordered pair. The ordered pair, the ordered pair of this point is 1 plus h, comma, f of 1 plus h. And, oh my, here is that secant line. Of course, I could draw further out if I wanted to. Okay, at first I didn't. I just wanted to focus kind of on the stuff inside. If I were to use this notation here, the slope of the secant line equals y1 minus y2 over x1 minus x2. Just to be very thorough, this point here is just the point 1 comma f of 1, right? And yes, I know f of 1 was 1/2. We actually calculated it. But the slope of the secant line is f of 1 plus h minus f of 1 all over 1 plus h minus 1, which equals f of 1 plus h minus f of 1 all over h, because here 1 negative 1 cancel. What do you notice, boys and girls? What is this? This looks a whole lot like something. This looks a lot like a difference quotient. It looks a lot like a difference quotient where x equals what? Where x equals 1. Yes, it does. This right here is a difference quotient. It's a difference quotient where x equals 1. Okay? Now, let's see. We said that as h approaches 0, as h approaches 0, we know that as h approaches 0, right, as this gap here closes, this secant line gets pulled closer and closer and closer and closer and closer. How can we write as h approaches 0? Yes, the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h equals, what is that going to equal? I know the slope of the secant line equals this. As h approaches 0, the slope of the secant line approaches a slope of what kind of a line? Yes, it approaches a slope of a tangent line. And notice here, I'm just writing the point of tangency, right? The slope of the secant line, and maybe we should be really, really thorough. Slope of the secant line over the interval of what, boys and girls? Of 1 to 1 plus h, right? That's the interval of x. This is the slope of the secant line, but as h gets dragged closer and closer to 0, as this horizontal gap closes and this point gets closer and closer and closer, we know the slope of the secant line over the interval of time from x equals 1 to x equals 1 plus h. This limit of this difference quotient equals the slope of the tangent line at x equals 1. Oh my, and here is your limit of a difference quotient. So you're wondering maybe, what does a limit of a difference quotient describe? Well, the limit of a difference quotient describes the slope of a line tangent at x equals whatever the point of tangency. And you also know that the slope of the tangent line represents what kind of rate of change. This represents what kind of rate of change? It represents an instantaneous rate of change. Okay, let's be thorough. Slope of secant line, which equals this, this equals an average rate of change. And let's make sure we're really thorough. An average rate of change over the interval of x from 1 to 1 plus h. This slope of the tangent line represents an instantaneous rate of change at, not over an interval, right, at x equals 1, which is the point of tangency. How did you like that? I hope that was like phenomenally, I hope that was fun. Well, you know what? Here's the thing, boys and girls. Since we know what f of x is, we're going to calculate this limit of a difference quotient. Why not? Because we know that f of x was, f of x equals, what was it? Is it 1/2 x squared? Yeah. All right. So let's calculate this limit of a difference quotient. This becomes the limit as h approaches 0 of f of 1 plus h. 1/2 1 plus h squared minus f of 1 is 1/2 all over h, and I definitely know and expect it's going to be 0 over 0. I'm going to leave it to you. Go ahead, you bang this out, mess it out, mash it out, you tell me what you get. All right, here it is in black, everyone. We know it's 0 over 0. I squared out 1 plus h, which is right here. Distributed the 1/2, we're right here. Look at the red. I cleaned up 1/2 and negative 1/2. I have my limit. Oh, still 0 over 0. Cleaned up, factored h out, cancel, cancel. I got 1. Now, up until this moment, we would have left this as 1. But this number 1 has context. And what is that context? Yes, blisters on your hand as a function of day. But this is an instantaneous rate of change. And this sentence is so very important. This means that on day 1, on day 1, the blisters on my hand are changing And actually, since this number is positive, I can say increasing, right? At the, what kind of rate? At the instantaneous. At the instantaneous, need to have this word, rate of, here it is, what's this number? 1, what's the units? Blister per day. Please know this is just pure coincidence that this ended up being a 1 on day 1, okay? And that is a wrap. The whole conversation here, it started with limits in slightly different forms, and then it went to talking about rates of change, and then we talked about average rates of change, secant lines, tangent lines, difference quotients, limits of difference quotients, and at the end of the day, we have taken our work with limits and contextualized it, placed it in the context of rates of change. And in this case, because I was feeling particularly, I guess, gross, I gave you a context that involved blisters over the course of days. All right, and for homework tonight, you will be asked to find some limits, evaluate some limits. You may be asked to find some rates of change given some context. You may be asked to calculate an instantaneous rate of change at a particular point of tangency or at a particular moment, right? Now you know how to do that. And that, everyone, is the lesson for today, Friday.